Stuff full. No. Good morning, all.
Hello.
I am Mrs. Sarbasrinath, Assistant Professor, Department of Chemistry, GC College, Silchar, and the convener of this webinar on recent development in the characterization of nanomaterials conducted by the Department of Chemistry, GC College, Silchar, Assam. Welcome you all. This college, GC College, is the premier college in the northeastern part of India. The DC College was established in the year 1935 and the Department of Chemistry was established in 1949. It has completed its 71 years. In these 2 days national webinar, we have with us two eminent speakers. Dr. Ratan Das, Department of Physics, Tripura University, Tripura, and Professor Chiraranjan Bhattacharjee of Department of Chemistry, Assam University, Silchar. I think this webinar will enrich everyone. Once again, I welcome you all. Now I request the patron of this webinar and principal of the college, Dr. Vivas Bhatt sir, to formally inaugurate the session and deliver his valuable speech. Thank you, sir. Sir, please. Vivas Bhatt sir, sir, please.
Yes, good morning. Good morning.
Good morning, sir.
Good morning, sir. And welcome.
Good morning. Yes, respected convener, Dr. Sarbasrinath, co-convener, Dr. Subhash Devnath, senior most faculty member in the Department of Chemistry, Dr. Tushar Devkanango, head of the department, Dr. Krishna Chandra Das, Dr. Joydeep Pal, and also other members. And our two speakers, renowned speaker, Professor Chiraranjan Bhattacharjee, Department of Chemistry, Assam University, and Dr. Ratan Das, Assistant Professor, Department of Physics, Tripura University. And my dear colleagues, scholars, students, and participants. First of all, I, on behalf of Gurucharan College, Silchar, and on my behalf, welcome you all in this 2-day webinar organized by Department of Chemistry and Internal Quality Assurance Cell, Gurucharan College, Silchar. On the topic, recent developments in the characterization of nanomaterial. So it's a great opportunity for all the teachers, scholars, and students to hear from two renowned resource person, Professor Chiraranjan Bhattacharjee and Dr. Ratan Das. We are really very happy that they have responded to our call in this 2-day webinar. During this COVID-19, everything become very much difficult with reference to education, higher education, especially the collegiate education and the university education. But our college fraternity, that is especially IQSC, Guru Charan College Silchar, develop, develops a online YouTube channel in the name of GCC Academia, through which all these activities, online activities such as invited talk, webinar, then other seminars, and that is classroom coaching or teaching is also going on. So I thank the Department of Chemistry for organizing this type of webinar today, national webinar, inviting two great personalities. Department of Chemistry is carrying out their tradition since long that they are organizing different types of activities, awareness program, quiz program, then research work, then this type of seminar. Last day I got a call from Abhijit Nath and he told me that as an inaugurator, I should join in this webinar. And accordingly, I thought that it is a pride for me, proud privilege for me to inaugurate this program. And I wish this today a national webinar will be a grand success and all the participants, right from the teachers to scholars to that is the students will be benefited from them. I once again thanks these two renowned speakers for today's topic and all the organizers headed by that is Dr. Krishna Chandra Das and all his team for making this today webinar a grand success. With this, I would like to conclude. Thank you once again. Namaskar and Jai Hind.
Thank you, sir, for your inspiring and valuable words. Once again, thank you, sir.
Thank you.
Now I call upon our HOD, Department of Chemistry, Mr. Krishna Chandra Das, to say a few words on this auspicious occasion. So, sir, please, over to you, sir.
Thank you, madam. Am I audible?
Yes, sir.
A very good morning to you all. Respected Principal, Disciple Shilcher, Coordinator IQSC, Honorable Speakers, Convener, Co-Convener, and all other departmental colleagues, and most importantly, the esteemed participants of the virtual gathering. On behalf of the Departmental Chemistry, GC College Shilcher, I express my heartfelt gratitude to all the participants who have registered their participation for this today's national level webinar on recent development in the characterization of nanomaterial. I once again welcome everyone in this novel gathering. This is the first time we are holding this webinar when all the class works and the interaction among the teachers and the students are totally suspended due to the grave situation of COVID-19 pandemic. With exponential growth and development in the field of science and nanotechnology, our students and the present researchers are getting the fragments of the different innovative practice in different fields, which promotes quantum jump in knowledge procurement. In the context of development, nanoscience and nanotechnology plays an imperative role which becomes the key features in the arena of advanced level trends in the modern scientific research. Nanomaterials have been around along with humanity for last 10 decades since the first step of their artificial production. Some nanomaterials are observable in the natural settings. Nevertheless, a lot of nanomaterials are developed and engineered to have a specific purpose or to meet a specific interest. Nanomaterials are applied to diverse fields of life, including cosmetics, sunscreen, sporting goods, advanced clothing manufacture, automotive industry, electronics, and others. The special interest is paid by the healthcare as nanomaterial contributes to improve diagnosis, image generation, and drug delivery purpose. Considering these above aspects, we have planned to listen from our experts about the recent development in the characterization of the nanomaterial and their thoughts, works, and findings in the field of nanoscience and nanotechnology, which will definitely strike our young mind to spark their hidden potential with a new enthusiasm. I hope this webinar will be more resourceful with a wide spectrum of new ideas. I request every participant to listen our resource persons and to interact with scientific department after this session. I once again welcome everyone for this national level webinar with gratitude and warm greetings. With this, I conclude here. Thank you. Thank you very much. Over to our convener, madam.
Thank you, sir. Thank you, our HOD, sir, Krishna, sir. Now, it is the time to introduce our today's speaker, for whom we are eagerly waiting. So, a brief introduction will be given by our departmental faculty, Dr. Jaideep Pal, sir. So, sir, please read out the introduction of our resource person. Sir, please.
Namaskar. Good morning to one and all present. It's a privilege on my part to introduce before you with a short biodata of our most esteemed resource person, Dr. Ratan Das. Dr. Ratan Das did his PhD in physics from Assam University, Silchar in 2012. Prior to that, he did his MSc and MPhil in physics from the same university in the year 2005 and 2008. Thereafter, he joined as assistant professor in the Department of Physics, Tripura University in 2012. Immediately after his joining, he established the Nanophysics and Nanotechnology Research Lab in the Department of Physics at that very same university. His field of research work includes synthesis, characterization, and application of various types of nanomaterials, especially noble metal nanocrystal, semiconductor nanocrystal, and magnetic properties. His research interest lies in the field of nanophysics and nanotechnology, with special emphasis on optical, elastic, and magnetic properties of differently synthesized nanomaterials. He also works on photoluminescence, FTIR, band gap study, phase transition, as well as defect creation in materials through swift heavy ions irradiation, plasmonics, as well as nanomagnetic research, resonance study. He is also engaged in the study of magnetic properties done by neutron diffraction method. His work finds application as sensors, antibacterial activity, LED, biofertilizer, soft ferrite, and magnetic applications. He is also specialization in X-ray diffraction patterns. Our esteemed resource person has already published 56 research articles in various peer-reviewed national and international journals. Also, he has attended more than 40 as well as national and international seminars and conferences. Under his guidance, one student has already been awarded with a PhD degree. One scholar has recently submitted his thesis. Four PhD research scholars are presently working under his guidance. Last but not the least, currently he is the project director of two major research projects and two minor research projects funded by SERV, BST, IUSC, BARC, and the total grant of all these projects is nearing 1 crore. So with this few words, I would now like to hand over to Sarvasri ma'am. Thank you.
Thank you, Jaideep, sir. Now the deck is over to our speaker, sir. So, sir, please, Ratanda, sir, the deck is over to you, sir. Sir, please.
Thank you very much, Joydeep sir, for your kind introduction. Am I audible?
Yes.
Yes, sir.
Yes, sir. Yes, sir.
Okay, thank you. At the beginning, respected patrons of this webinar, Dr. Vivash Dev, Principal, GC College Silchar, respected Chairperson of this webinar, Dr. Rajashri Pal, Coordinator of IQSC, GC College Silchar, Convener, Ms. Sarboshi Nath, Chemistry Department, GC College Silchar, and co-convener Dr. Subhash Devnath, Department of Chemistry, GC College Silchar, along with the most senior faculty member of the chemistry department, Tushar sir, Joydeep sir, Abhijit sir, Dr. Suhas Dev. Good morning to all of you. At the beginning, I want to say that I was a student of this GC college, and I felt very proud that today I am presenting my lecture in this webinar. And at the same time, I want to say that it is a great proud moment that college Department of Chemistry is organizing a webinar on the recent trends in characterization of nanomaterials. So thank you very much. Thank you all of you for giving me a chance in this webinar for giving a lecture on characterization of nanomaterials by XRD and atomic force microscopy. So can I share my screen or?
Yes, please share. Please share your.
Please share. Please share.
Hello. Sorry, there was a network interruption. We are back.
Yes, please share.
Yeah, there is a screen share option. This is the screen share option at the bottom of your screen. Yeah. You can share the entire screen. Right now I am taking everyone on backstage and we'll begin with
Is it visible? Hello? Is it visible? Krishna sir? Krishna sir?
Yes, sir. Hello.
Is it visible?
Yes, it is visible.
Okay, thank you very much.
Is big screen of course.
And you can hide that pop-up message. Yeah, now it's okay. So participants can see your screen, your slideshow as well as your video. So I'm putting the organizers on backstage, so you can see it.
Okay, let me start.
Yeah.
So this is a 2 days national webinar on recent developments in the characterization of nanomaterials, organized by Department of Chemistry in collaboration with IQSC GC College Silchar, Assam. The topic is characterization of nanoparticles through X-ray diffraction analysis and atomic force microscopic study. I want to again ensure, Krishna sir, am I audible and screen is visible?
Visibles.
Yes, sir. Yes, sir. You're audible.
Audible and visible.
Okay, thank you, ma'am. Okay, let me proceed. Again, I want to say that the topic of the webinar that I am going to present is characterization of nanoparticles through X-ray diffraction analysis and atomic force microscopy. Myself, Dr. Ratan Das, Assistant Professor, Department of Physics from Tripura University, Tripura. So at the beginning, I want to say that regarding nanotechnology. Nanotechnology, more or less, we can say started its journey from 1990 onwards, and it is because of the availability of many sophisticated instruments like electron microscope, tunneling microscope, X-ray diffractometer. Because of the availability of many sophisticated instruments, nanotechnology has started its journey, rather I can say, but much before, many renowned scientists also prepared nanoparticles earlier, but they could not able to study the nanoparticles or size, shape or other properties because of the non-availability of sophisticated instruments. We are in the era where these sophisticated instruments are available. That's why nanotechnology started this journey, and we are able to apply the nanoparticles in different field or different branch of the science. Now, the question is how small a nanoparticle is. I can say that we as a researcher, we deal with the nanoparticles in between the range 1 to 100 nanometer, because in this range of 1 to 100 nanometer, nanoparticles show is various beautiful characteristics, properties, and also with these properties, it is applicable in different branches. And now, broadly, I can say that nanoparticles are smaller than bacteria or comparable to the size of the virus or less than that. Because viruses has a size around 100 nanometer, but we deal with the nanoparticles which are below 100 nanometer, around 20 nanometer or 30 nanometer nanoparticle. Actually, we generally deal with. So again, I want to say that nanoparticles are very small. They are smaller than virus and bacteria as well. So with this slide, I can say that with this slide, we can compare the nanoparticles. We can compare the nanoparticles with other structures, available structures. Suppose DNA is 2.5 nanometer, helical ring is 2.5 nanometer, red blood cell is 5000 nanometer approximately, I am not sure. But compared to all these, you see nanoparticle is 1 to 100 nanometer, and within this range of size range, we actually deal with the particle and we apply this particle. Again, I want to say that generally we deal with the nanoparticles which has the average size of 20 nanometer or 30 nanometer or 40 nanometer. I want to add that even smaller than 100 nanometer particle we actually deal with. Now, what are the sophisticated instruments that are available for characterization? I have already told, but there are electron transmission microscope, scanning electron microscope. These two topics will be covered by our next renowned person from chemistry department, Professor Chiraranjan Bhattacharjee, tomorrow. I shall cover here the X-ray diffractometer, X-ray diffraction, and atomic force microscope. And as well, there are some optical characterization is required, such as UV visible spectroscopy, photoluminescence spectroscopy, Raman spectroscopy, and FTIR. There is scanning tunneling microscope, and there are SQUID and BSM. These are required for magnetic characterization. Now, what is the characterization? Characterization is nothing but knowing about the properties of the nanomaterials or nanoparticles. If we do not know the properties of the nanoparticles and nanomaterials, suppose the size, the shape, the optical properties, the magnetic properties, or the crystallinity, the structure, internal structure, crystal structure, we cannot apply the particular nanoparticle for special application purposes. So before going into application purposes, we need to know the properties or basic characteristics of the nanoparticle. That's why we need the characterization of the nanoparticles through these sophisticated instruments. So these are the minimal sophisticated instruments that are required for characterizing the nanoparticles before application purposes. Now, I want to again emphasize on the fact that TEM and SEM, transmission electron microscope, scanning electron microscope. These are required for to view the nanoparticles, what are the size, what is the shape, as well as TEM and SEM also provides the crystal structures also. Especially TEM provide the crystal structure through SAD pattern, SEM provide the composition through EDX. So this will be covered by tomorrow's renowned person, Professor Chirananjan Bhattacharjee. XRD, through XRD or NMR, we can determine the structure as well. UV visible for optical properties, AFM is required for surface structure, mechanical properties also we can study, and SQUID and BSM are required for magnetic property study. So these are the minimum sophisticated instruments that are required for characterization of nanomaterials or prepared nanoparticles. So what are the different ways of preparing nanomaterials or nanoparticles? There are physical method, there are chemical method, there are biological method also. Now, physical method is nothing but about going to the nano range from the bulk material. I mean, suppose if we etch the nanoparticles, I mean, if we etch the bulk particle through lithographic technique, we can go to the nano range. I mean, we are going from the top to bottom range. Means bulk to the nano range, we are going through physical method. There are ball milling, there are vapor phase, there are thermal evaporation methods through which we go to big size to the nano size. Chemical process is nothing but arranging the atom or accumulation of atom and thereby making some process through which nanoparticles can be prepared atom by atom. So accumulation of atom by atom arrangement is the chemical process through which we can arrange or we can prepare the nanoparticle. There are wet chemical method processor, there are Sol-Gel processor, there are different chemical processor there which I haven't included. But generally solution based method or wet chemical based method we follow in the chemical process. There are biological process such as we use some plant extract for the preparation of nanoparticles. There are also some chemical reaction takes place, but in that reaction process we use the plant extract. The plant extract actually acts as a oxidizing or reducing agent as well as capping agent for stabilizing the nanoparticle. There are some proteins and enzymes are there through which they are useful in the biological preparation of nanoparticles. Now, after preparing the nanoparticles, again I am telling you the fact that after preparing the nanoparticles, you need to know about their size, shape, and crystallinity of the sample, whether the sample is crystalline, whether the sample is amorphous or not. That we need to study. And here we use X-ray diffractometer is for crystallinity and purity of the sample. Electron microscope is used for size, shape, and crystallinity of the sample. We can visualize the particle through electron microscope. But using X-ray diffraction data, we can also determine the average size of the particle that we prepare through chemical process or through physical process or through biological process. Now, atomic force microscopy is another very sophisticated instrument which is used for morphological study, I mean size, shape, the surface structures, height profile of the thin film. So, here I shall cover the X-ray diffractometer and the atomic force microscope a little bit. If I get time, I shall try to give you the details about atomic force microscopy. Now, going into the X-ray diffractometer, this X-ray diffractometer provides us the crystalline nature or amorphous nature of the sample, and also it gives us the phase purity, whether a sample is pure or not. That we can also know from the X-ray diffraction study of the prepared sample. Now, before going into the X-ray diffraction analysis, there are some basics things, basic knowledge are required to know. What are the basic knowledge? You have to know about the crystal structures. You have to know about the primitive cell, unit cell, and as well as the Miller indices, crystal planes, crystal direction, reciprocal lattice, case space, brilliant zone, the Bivas lattice, interference and diffraction, a wall sphere, and structure factor. I don't have all the details because it is not possible to cover all the details in a single lecture, and otherwise the subsequent all the things will be I have to miss. So let us consider that the students should know about all this. I know the Ewald sphere, structure factor, billion zone, these are a bit difficult or to understand, but still before going into the X-ray diffraction analysis, we need to know about all this basic knowledge, especially Miller indices, crystal planes, crystal direction, Bravas lattice, and structure factors are required to know about or to go for X-ray diffraction analysis. So just I want to say that the structure factor is very important in the X-ray diffraction analysis part, where later I shall discuss a little bit. But let us see that in the Bravas lattice structure we have a simple cubic or a simple or body centered or face centered structures, and in the case of a simple structure all the reflections are available. But in the case of body centered, where HKL, the Miller indices, which is even, those will be available in the X-ray diffraction pattern. In the case of face centered, the HKL, unmixed, and all odd or all even, this particular HKL, I mean the X-ray diffraction data or X-ray diffraction structure which contains the odd or even HKL values that are available in the case of face center. So reflection necessarily absent in the case of simple is none, all are available. In the case of body center, this HKL where it is becoming odd, these are not available, these are absent. And face center where HKL mixed, I mean odd even are there, this is not possible. So these simple things you have to know about this in the case of analysis of the X-ray diffraction data. So what are these HKL actually? HKL is nothing but our Miller indices. So this Miller indices you have to know beforehand before going to the X-ray diffraction analysis. So these are some examples of permitted reflection. Here you see all the Miller indices, all the reflection planes are available. But in BCC you see 100 is not available, but 110 is available. In the case of a FCC, that 111 is actually available. So these are the things in the structure factor. I mean structure factor provides this particular arrangement where the available I mean these particular planes are available in the X-ray diffraction pattern. If these are available, then you can say that our structure is either simple cubic or body centered or face centered structure. Now let me say about the X-ray diffractometer. This is one particular X-ray diffractometer instrument, and it is actually we mount the sample here. And what are the samples we require? Either we require powder sample or a thin film sample. But there are some separate instruments which are for single crystal arrangement. See, I mean the materials which are single crystal in nature. For those single crystal nature materials, we go for different types of X-ray diffractometer. But generally, powder sample or polycrystalline nature of powder sample or thin film or polycrystalline nature sample, we use the general X-ray diffractometer. And X-ray diffractometer relies on the dual or particle wave nature of X-rays to obtain the information about the structure of crystalline nature. Actually, in the X-ray diffractometer, why it is X-ray diffractometer? Because in the X-ray diffractometer, we apply the X-ray, we incident the X-rays into the sample, and we study the scattered rays actually from the sample. And studying the scattered rays, we may know about the information or about the size, about the crystallinity of the sample that possesses actually. The primary use of the technique is the identification or characterization of compound based on their diffraction pattern. So X-ray diffractometer actually gives us the diffraction pattern. When we throw X-ray into the sample and after scattering taking place, some diffraction pattern we see. But before going into this part, I want to say that sometimes in the X-ray diffractometer we say the reflected rays or diffracted rays. Both the term actually we use. Diffraction is taking place through the nanometer range below the surface. I mean the diffraction taking place from the sub-nanometer or angstrom nanometer range of the surface or below the surface, the diffraction taking place. But actually, reflection is taking place from the surface only. But even though we many a times we said that reflection is taking from the surface in the X-ray diffractometer. I do not know why people use the term reflection, but in many literature or many articles you will see that the term reflection is generally used. Now in the X-ray diffractometer instrument, there is a goniometer. This goniometer is very it is the main part of the instrument actually. In the goniometer goniometer is an instrument that either measures the angle or allows an object to be rotated in a precise angular position. So here you see that sample that place or mounted in this particular place, and X-ray from the X-ray tube, X-ray falls on the sample and it get scattered through in various angles. And this particular detector actually moves or get rotated in this particular circular path, and it collects the scattered rays at a particular angle. We get more intensity in the scattered pattern, and that more intensity we obtain because of the interference, or rather we can say diffraction pattern that takes place actually. So this is the detector, which is a monochromator, and there are the X-ray tube from which X-ray falls on the sample actually, and the whole part of the instrument is called a goniometer. Now here see from the source light rays falls on the sample, and it then goes to the detector after scattering, and the detector measures the diffraction pattern or scattered pattern. So the principle of the X-ray diffraction is nothing but regarding with the Bragg's formula. We know in the diffraction pattern, this Bragg's formula gives us at where we shall obtain the higher intensity rays. So it is twice the sin theta n lambda. N is the order of the reflected rays. D is the lattice spacing. You see here that particular straight lines are lattice spacing. All of us know this, and these are the planes actually. The planes may be 110, or 100 or 110, or any pattern of the planes from which the reflected rays, or rather you can say diffracted rays, after scattering, they may at a particular angle, at a particular twice theta angle, you see there is a twice theta, and theta is the grazing angle actually. So the incident rays makes an angle twice theta with the detector actually, and at a particular value of twice theta, this diffracted rays makes some interference pattern, or rather we can say a diffraction pattern, where they satisfy this Bragg's formula twice the sin theta n lambda. Thereby we get the diffraction pattern at a particular angle, and it is not due to the single plane. If there is a single plane, then it is a single crystal structure. But in general, in a crystal, we have many diffraction planes. Many planes will be available, as I have told you earlier. So different planes give different peak position in the XRD. That peak position means where higher intensity of the diffraction patterns are available. Now different planes give different peak position means different planes at a different plus theta angle gives the diffraction pattern, and at a particular angle we shall get higher intensity. Then suppose at 30-degree angle we shall get a particular peak position or higher intensity. Then at another angle, suppose at 40-degree angle, due to another particular plane, we may obtain another diffraction peak or the higher intensity because of the satisfactory nature of Bragg's formula twice d sin theta n lambda. So what I want to say that different planes gives us different diffraction pattern because of the making of different angle with the detector by the different planes. Now, in that particular diffraction pattern, one very important formula is what is known as Scharer formula. Through this Scharer formula, we can determine the crystallite size or nanoparticle size. Okay, so I shall go into the details later, but let me tell you that this Scharer formula is D is equal to K lambda beta cos theta. What is that theta? Theta is nothing but that twice theta of theta. Here the incident ray makes an angle twice theta with the detector, and that at the angle of twice theta we shall obtain the diffraction pattern, and from the twice theta angle we can obtain the theta, and we can place the value of theta here in radians. D is the average crystallite size or size of the nanocrystals. Lambda is the X-ray wavelength. Here, in the X-ray diffraction pattern, we use the X-ray of a particular wavelength. But I shall explain later. In some pattern, we shall differ a varying wavelength. But generally, we use X-ray of a fixed wavelength and putting the value of that wavelength and beta is nothing but our full width and half maxima that I shall explain in my subsequent slides. And K is a particular Scharer constant which depends on the shape of the particle. If it is spherical, then we shall use approximately the value 1 or 0.93 or 0.9. And putting all these values, we can obtain the nanoparticle size actually. I shall explain it in my subsequent slides, but beforehand I want to introduce this particular Scharer formula because this is very important in calculating the size of the nanoparticle in the X-ray diffraction pattern. So what I want to say you that the different planes present in the sample provides different diffraction peaks in the X-ray diffraction pattern. So this is the single crystal specimen show only one family of peaks. I mean this is a single crystal having with one planes, and they will provide only one particular peak. But we are interested in polycrystalline nature because most of the nanoparticles are polycrystalline in nature. So a polycrystalline sample have different crystallite size or different planes available in that particular structures, and we shall obtain different planes. You see, this is a pattern, arbitrary pattern that are given actually in the data. So here in the figure, here you see at a particular angle of 21 degree, we have obtained 100 plane. I mean, because of the presence of 100 plane, the diffraction pattern with most of the with higher intensity is available at a particular angle. Next pattern is available at another angle with 100 plane. But at this particular angle, no way other plane will come into exist. Different plane will give different diffraction pattern at different angles. Now you see, there are different diffraction methods. One is Lao's method, rotating crystal method, powder diffraction method. I don't want to explain it here, but what I want to emphasize is that emphasis on the fact that in the Lao's diffraction pattern, we use variable wavelength of X-rays. But in the case of crystal structure determination or powder sample, we use the fixed wavelength of X-rays, and the angle is varied. But here in large diffraction pattern, you see angle is fixed. So we are more interested in powder diffraction pattern or rotating crystal method, where we use the fixed wavelength of X-ray, and we throw this particular fixed wavelength X-rays into the sample that gets scattered, and we obtain X-ray diffraction pattern. And you see in the single crystal, in the case of a single crystal, we use rotating crystal method. And I want to say you that the arrangement of the X-ray diffraction is the arrangement of the X-ray diffractometer, where many sort of rotating methods are there. The powder sample method, we have two rotating circles are there, where we rotate the goniometer in two different directions. But in rotating crystal method, we have four rotating circles are there. So different X-ray diffractometer has different methods of acquiring the diffraction pattern. But that powder sample or thin film sample where we use that particular X-ray diffractometer is very useful and very easy to handle actually. Now another important part is that whenever the particular sample is crystalline in nature, we get this sort of X-ray diffraction data, where different peak position will be available associated with different planes. But it is if it is a liquid sample or amorphous, this is very important. If it is amorphous, then we never get such peaks in the diffraction pattern, and we get a huge big hump in the diffraction pattern. No way we can get any sort of this small peaks in the diffraction pattern. If such sort of small peaks are not available in the diffraction pattern, then we can certainly say that the prepared sample is amorphous. See, as a nanoparticle researcher, I want to say that I generally use I am interested in the structure where the sample is crystalline in nature. But there are other researchers, those who study in the amorphous nature of the sample, they will be happy if they get a pattern like this. So with the researcher, we want to analyze the crystalline nature of the sample or different structure of the sample. We are happy if we get a structure like this, having different planes, having different peaks. But there are researchers, they will be happy if they get a amorphous nature of the diffraction pattern. If they get the crystalline structure, they will throw the sample. They again prepare the sample to get a amorphous structure of the amorphous nature of the sample. Now, this is an example of the silver nanocrystal X-ray diffraction pattern of silver nanocrystals, which is the pattern that we have obtained in our prepared sample. You see, in the X-ray diffractometer, in the X-ray diffraction pattern, we have obtained various peaks in the sample. So many peaks are available actually. And in the peaks, you see one peak is having very narrow in width, but another peak is showing some width. So this width is very important for us, for researchers like us. And this particular pattern actually shows that the silver that we have prepared, silver nanoparticle that we have prepared, is crystalline in nature. And another thing I want to say that below this particular pattern, this is the background pattern, and this is also very important, because background pattern you have to know. In later of my slides, I shall explain the requirement of the background nature actually, and from the background nature we can obtain many things. Right now I don't want to say, but I want to say that this background is very important also. and with reference to the background, we measure something. We measure the intensity actually. Now, regarding the phase indexing, what is the phase indexing? Phase indexing is nothing but associating the mirror indices with a particular peak. So there is a phase indexing techniques in Laws diffraction pattern. We obtain many circles actually. I don't have any slides with that particular pattern here. But in Laws diffraction pattern, we have different circles, and from the center of the circles, if we measure the radius, and through this technique, we can use in indexing the diffraction pattern. And there are some other mathematical technique also in the case of outer samples where we use the phase indexing techniques actually. But there are some crystallographic database, what is called CIF files. Now, matching with those crystallographic database, we can matching the obtained obtained X-ray diffraction pattern with this crystallographic database. We may index. We may go for matching, or we may say that our sample is matching with that particular sample. That's why our sample is of that nature. Suppose I have prepared as silver nanocrystals, and for a particular silver nanocrystals, the pattern is fixed. You know, suppose what I want to say you that here I have obtained many diffraction pattern in case of our silver. But if you prepare silver nanocrystals, you will find that some of the peaks may be missing, but major peaks, suppose 1 peaks, 2 peaks, that will be available at a particular angle. So that is fixed, and that is the characteristics of silver nanocrystal. Suppose what I want to say is that 1 plane of silver nanocrystal is that we have obtained around 15-degree angle, that is fixed. That particular plane cannot be obtained at 55-degree angle. So if we obtain the 1 plane at 55-degree angle, then it is no way the silver nanocrystals actually. So silver nanocrystals shows 1 pattern around 15 degrees angle of cos theta angle, and 2 plane around 35 or 33 degree angle. So matching with the crystallographic database, we may index our pattern actually. So there are some crystallographic database which contains a list for thousands of crystallographic phases. This database are some ICDD software, JCPDS software, powder diffraction pattern PDF. This is not the PDF file that we shall say. It is a powder diffraction file, and these are some costly softwares. But these are available in different libraries, or these are available with the instruments where a X-ray diffractometer instrument is available. Now they supply they're matching with those pattern. They supply or they study, or if you are present in that particular instrument near the instrument, then you can also match your sample with the particular pattern. And with matching with this particular pattern, we can index our diffraction data. Now going into the next part, as I have told you that base of the X-ray diffractometer is very important, and this is the base actually. This is a schematic diagram though, but this is the base and this is the highest peak position, and there is some width that we obtain in the case of a particular X-ray diffraction pattern. Now the width is very important. Okay, the peak position may be obtained at a particular diffraction angle of twice theta. Another thing that I want to say is that suppose if we study the X-ray diffraction pattern of an ideal bulk material with infinite size bulk material, we obtain the diffraction pattern which is infinitely peaked. Rather, I can say it is the ideal delta function. Delta function is the infinitely peaked with no width actually. And this is the ideal diffraction pattern that we obtain in the case of a big bulk sample in the X-ray diffraction pattern. But if we go into the smaller size in the nano range, then there will be some, you will observe a width that you will obtain in the X-ray diffraction pattern. Okay, so what I want to say you that the size play a role in broadening of a diffraction pattern. And going back into the slide that I want to show you that what Sharar obtained a formula D is equal to K lambda beta cos theta, where beta is our full width and half maxima. So higher the fluid, smaller is the size. Okay, this is very important. That's why I have beforehand I have told about this this particular Sharar formula, because D is inversely proportional to beta. Beta is our full width at half maxima. Let me explain what is full width at half maxima. Full width at half maxima means this is the height of the pattern from the base, and at half maxima, this is the full maxima and the half maxima. That's why we are saying that full width at half maxima. At the half maximum, I mean half of the intensity of the diffraction pattern, the full width is beta actually. So that beta is nothing but full width at half maxima, and the size of the nanocrystals or crystalline size is inversely proportional to the full width at half maxima. The size, if the full width and half maxima is more, if the more the width, the smaller is the size, and the smaller is the width, the higher is the size. Okay, so for a bulk sample, it is very infinite in size. So we generally obtain the ideal delta function with no width generally. Okay. So again, I want to tell you that this is very important for the beginners actually. Those who know, it is very simple for them. But those who do not know, this is very important, because full width and half maxima play a very big role. Smaller the size, higher is the full width and half maxima. Higher the size, lower the full width and half maxima. Bulk sample shows the infinitely peaked diffraction pattern with almost no peak. But the instrument plays a role in broadening the diffraction pattern, what is known as instrumental broadening. So there will be if you take a bulk X-ray diffraction pattern of the bulk sample, there may be a chance that you may obtain some width in the X-ray diffraction pattern in a particular one peak. So this generally happens because of the instrument, because we need to calibrate the instrument. The instrument plays a role in broadening the X-ray diffraction pattern. So for this, what we do generally before starting the sample or before doing the X-ray diffraction pattern of the sample, we generally place a known sample, suppose silicon sample. Generally bulk silicon sample is used, and we take the X-ray diffraction pattern of the bulk silicon sample, and from that bulk silicon sample, if we find any width, we adjust, we measure the width of that bulk silicon sample, and we note down that particular instrumental broadening or the broadening for bulk silicon sample. Then we place our sample which needs to be studied. Which needs to be studied. and then we get the X-ray diffraction pattern of the sample that we want to study, and then we subtract the instrumental broadening from the obtained broadening of the sample, and thereby we just get rid of the instrumental broadening. But at the same time, I want to say that not only the crystalline size, but crystalline size plays the role in broadening the X-ray diffraction pattern, but the strain also. I want to emphasize on the fact that strain also plays a big role in broadening the crystal, nanocrystal especially. Why the strain is coming into the picture? It is not the external strain actually. In the when we prepare the nanocrystal, we generally confine the system in a very small range. Suppose we have a 10 nanometer nanoparticle. Then we all the electrons, all the materials are confined in a very small place. So the arrangement that suppose if we have prepared silver nanocrystals, the arrangement of the atoms in the bulk silver is not the same arrangement you obtain in the nanocrystals, because some sort of distortion will take place in the arrangement, and that distortion actually put a strain into the sample, and that strain is our intrinsic strain, internal strain actually. That intrinsic strain, because of the rearrangement of the atoms, different, which is different from the bulk sample, that produces as intrinsic strain, and because of this strain, we get some extra broadening in the X-ray diffraction pattern. So as a whole, I want to say you that the crystalline size as well as strain plays the role of broadening the X-ray diffraction pattern. So the broadening that we obtain in a particular X-ray diffraction peak is actually nothing but due to the effect of strain as well as crystallite size. But there are other effects also. Instrumental broadening, I have told, crystallite size, I have told, and the strain also I have told. But because of the presence of some defects or suppose if we dope the sample, if we have a semiconductor sample and if we dope the sample with other atom, then that arrangement also get distorted because of the doping, and again some strain comes into extra strain that comes into effect, and that's why the extra broadening we may obtain. And what happens that if we dope the, let me go into the next slide. I shall tell about all the details in later of my slide. So what I have told you about that, in the X-ray diffraction pattern, we have instrumental broadening. That instrumental broadening we may get rid of from the measured broadening, and we can obtain a particular suitable broadening after getting rid of that the instrumental broadening. And in the X-ray diffraction pattern, I have told about that crystalline size, strain also plays a role in broadening the X-ray diffraction pattern. So what is called residual strain, or we may say it is the intrinsic strain arising because of the dislocation or some staking faults or other defects. Okay, so all the factors are coming into the picture, but bigger role plays the size and the strain actually into the X-ray diffraction line broadening. So the term is very important, X-ray diffraction line broadening. Line broadening means infinitely peaked sample, infinitely peaked X-ray diffraction pattern in the case of a bulk sample that gets broadened when we decrease the size to the nano range. Okay, and in the nano range, some extra strain is coming into the picture because of the rearrangement of the atoms in the small region, what is called size effect, or that you can say what is called confinement effect, that you can say. So because of the confinement effect, because of the size effect, we can obtain or we can see, or we can observe some sort of broadening in the X-ray diffraction pattern. So here you see this is the infinitely peaked pattern for a this is a schematic diagram though. This is the infinitely peaked pattern that we can obtain for a bulk sample, and this is the broadening of the X-ray diffraction pattern in the case of a nanoparticle sample. This is the maximum intensity. This is the half maximum intensity, and this is the width, I mean full width at half maxima. Half maxima means the half of the intensity of the X-ray diffraction pattern, and here lies the base. We do not, from the base is actually we measure the intensity from the base of the X-ray diffraction pattern, not from the axis. Okay. Again, I want to tell you that origin of this intrinsic strain is nothing but the size confinement of the nanoparticles and generation of vacancies, defect states, or rearrangement of all these things. Now, this intrinsic strain can be calculated, can be obtained. There are different methods. What are the different methods that I shall explain one by one? That is the Williamson-Hull method, Helder-Wagner method, size strain plot method, Warren-Eberberg method, and Boyd method. These are there are some complicated methods are there. There is a small, or rather I can say some easy method, Williamson-Hull method is there, through which we can obtain this intrinsic strain value. And earlier I have told that the Scharer formula can be used for calculating the size of the nanocrystals. The Scharer formula, basically Scharer formula is very important. Whoever deal with the X-ray diffraction pattern for nanocrystals, we generally use the Scharer formula for calculating the size. Okay. You see here, this is suppose a bulk sample where this is the lattice, lattice pattern, and it is the lattice distance d. But if we go into the nano range, then there may be increase in the lattice pattern, okay, because of the size confinement, and because of this expansion of the lattice expansion, rather I can say the peak position may get shifted. Okay, I shall explain why the peak position may be shifted to the higher twice theta range or lower twice theta range. But because of the size confinement, that may also take place. Because bulk sample may show you at a particular twice theta value, but because of the size confinement, there will be some shift of the twice theta value. And if we this is the uniform state, okay. Now if we dope the sample, there may be non-uniform strain in the pattern we can obtain, and that particular non-uniform strain also actually broaden the X-ray diffraction pattern. All these things are there, but lots of theories are there that I cannot explain. Basically, I am explaining the fact which should be known beforehand. Now there are complicated theories are there regarding all these things. Okay, there is a book that I have shown. The QTD book is there. If you go through that book, you can obtain all the details regarding X-ray diffraction pattern. Regarding X-ray diffraction pattern study is very vast thing. In a single lecture, I cannot cover all the things, but I shall cover the thing. I am covering the things which are very important. So there is a non-strain pattern, there is a uniform strain pattern, and there is non-uniform strain patterns are there for which the broadening actually takes place. let me emphasize on the fact of doping effect, because suppose if we have a the semiconductor sample or magnetic sample where we may dope the particular sample with many doping element, and when the doping element into the host material, if we dope with another material, there may be a difference in the ionic radius. So there are ionic radius differences are there. And because of these ionic radius differences, all the factors are coming into the picture. So substitution of dopant ions disturb the crystallinity of the sample, because an unknown sample you are putting into the place of a known sample. Suppose we have a CDS nanocrystal. If we dope with silver, then the silver nanoparticles at some places it will replace the CD. So there may be ionic differences, because ionic radius of the CD is different from ionic radius of silver. So we may have different types of dopant where ionic radius may be smaller, ionic radius may be larger than the host material. Okay, so because of the substitution, some compression or expansion of interplanar distance taking place. Now, as per Bragg's law, the scattering angle is inversely proportional to the interplanar distance, because Bragg's law, as per Bragg's law, where twice d sin theta, that particular d is coming into the picture. So that scattering is inversely proportional to the interplanar distance, which makes shifting of the peak position. Okay, so if we dope the sample, there may be compression or expansion of the pattern or interplanar distance takes place, and because of this expansion or compression, that particular shifting of the peak position takes place. Now there may be a question arise in your mind that it is a doping effect which is coming into the picture. But if we decrease the size without doping, if we decrease the size of a sample to the nanorange, suppose if we have a 10 nanometer particle, then in that case also some sort of disturbance in the crystallinity taking place because of the size confinement effect, and because of this some compression and expansion of either compression or expansion of the interplanar distance taking place, and thereby shifting of the peak position will take place. So higher angle side shifting of the peak increases with intrinsic stress inside the sample. Now, now the higher angle side, why I am saying is the fact that if the ionic radius is higher than the host material, then the expansion will take place. Okay, and in the case of expansion, the lower angle, I mean twice theta at a particular, suppose at particular 30-degree angle we are obtaining the twice theta value. At lower angle side we may obtain. But if the compression is taking place, then the higher angle side shifting will take place. So degree of these changes depend on the concentration, depend on the size confinement, and if the doping element or doping is very of low, sufficiently low concentration, then there may be you may not notice any change in the diffraction pattern, because it is not like that shifting will take place by a large amount. Shifting will take place by a very small amount compared to the your reference material. Reference material may be a bulk sample, reference material may be a pure nanocrystals, and after doping you may obtain a diffraction pattern. You may differentiate the two patterns. You may observe the difference, or you may not observe the difference. Okay, but generally we observe the difference in the diffraction pattern. If we compare a bulk sample with a nanocrystalline sample of the same material, or of the same material after doping, we may observe some differences actually. Now going into the next slide, what I want to tell you that X-ray diffraction pattern analysis is very important. Important in the sense that we may obtain the crystallite size, we may obtain the crystal structure, we may obtain the lattice plane, we may obtain the despacing, lattice constant, strain also we obtain, and using different models we can obtain the internal stress, internal energy density that exist in the nanocrystals. All these variables we may obtain from the single X-ray diffraction pattern. X-ray diffraction pattern, that's why is very important. No other instrument or no other study or characterization technique will not provide that much huge information regarding your sample. It is the only XRD that gives us huge information. If I have a X-ray diffraction pattern of a single material, then I can study so many things. So many things we can study. Except Raman pattern. Raman pattern similarly also gives us many information. But except Raman pattern, no other instrument provides that much information, or no other characterization technique provides that much information what X-ray diffraction pattern provides us. Now going into the main topic, till now I have explained what are the things that you can obtain in the X-ray diffraction pattern. Now I am going into the research part actually. So there are different methods for X-ray diffraction peak analysis. Suppose if we have a peak of X-ray diffraction pattern, single peak, we may go for X-ray diffraction peak analysis. Okay, so X-ray diffraction, this peak analysis of X-ray diffraction pattern will provide many information. Now, based on the broadening of the X-ray diffraction peak, already I have told you, but still many things I want to add here. Say the broadening of the X-ray diffraction peak, I mean, as I have told you, from the broadening we can obtain the strain, we can obtain the size, and the other information also. So based on the broadening of the XRD peak, there are methods of Williamson-Hall type, Helder-Wagner method, and variance method. But based on the Fourier coefficient of the X-ray diffraction peak, see, I want to say later also in my slide I shall say, but in this particular time, in this particular related topic, I want to tell you that the X-ray diffraction peak may be analyzed using the broadening of the X-ray diffraction pattern. But in the peak profile analysis, what we do generally, we just make some pattern of the peaks actually. What is the pattern? We place a particular function, we match a particular function with the peak. Suppose the X-ray diffraction peak may be a Gaussian peak. Okay, sometimes the X-ray diffraction pattern may be a Lorentzian peak, and sometimes there are also peaks which may be a combination of Lorentz pattern, Lorentz function pattern, or a Gaussian function pattern. Now, those Gaussian pattern or X-ray diffraction pattern, the Gaussian function of the X-ray diffraction pattern, Lorentzian function of the X-ray diffraction pattern, or the combination of these two, what is known as Boyer function. These functions may be we do the Fourier transform of those functions. Okay, and after doing the Fourier transform, we may obtain the Fourier coefficient of the X-ray diffraction peak. So, analyzing the Fourier coefficient through Warren-Eberberg method and Balzer method, we may obtain also different information. So, there are two techniques actually. Rather broadly, there are two techniques. One is broadening, full width and half maxima of the X-ray diffraction pattern, and Fourier coefficient of the X-ray diffraction pattern of the sample. So these are mainly two classes. One is that we deal with the broadening of the X-ray diffraction pattern, full width and half maxima, and another is Fourier coefficient of the X-ray diffraction pattern. As I have told earlier, that we may obtain the instrumental, get rid of the instrumental broadening through this formula. we may obtain the size through this Scharer formula. D is equal to 0.9 lambda, because here we have put the 0.9 the value for K, and that is for actually spherical nanoparticles. Okay, Stokes considered Stokes in 1953 considered deformation or strain induced during the preparation of the crystal structure. So Stokes gave the idea that the value of strain, I mean the strain value, how it affects the width, the beta, the width and half maxima in that particular width, the significant amount the strain is giving is 4 epsilon 10 theta. Don't ask me how you can obtain these things. This is not the now it is not the time to discuss about obtaining this particular 4 epsilon 10 theta. But take it granted that Stokes through various methods gave the idea that the strain value is 4 epsilon 10 theta, and he actually makes those beta strain and beta size in the Fullerton half maxima. He told that the Fullerton half maxima is a combination of the effect of size as well as strain, and this combination actually get reflected in the Williamson-Hall method. Williamson-Hall method considered the total broadening as a sum of size and strain induced broadening. So total broadening of the extra diffraction pattern is nothing but it is the convolution of size and the strain effect. So after some rearrangement of the values, we may obtain a formula like this: beta HKL. This HKL is related to a particular peak actually. Okay, so beta HKL cos theta, that theta is coming into the picture because of the cos theta value, is equal to K lambda by D. This is the this is coming into the picture because of the Scharer part, and this is the strain part. So this is nothing but our Williamson-Hall method, but this method is called as uniform deformation model. That uniform deformation model considered uniform strain. Uniform strain means throughout the crystallographic direction, there are direction of 1 plane, there are direction of 2 plane. So we consider at the beginning we consider uniform strain in every crystallographic planes. Okay, in every crystallographic direction. And considering that fact, we generally we generally plot a pattern with beta HKL cos theta along y-axis and 4 sin theta along x-axis. Okay, and for every plane we put the values. Okay, and then we obtain a straight line from the intercept of the straight line. The intercept is nothing but K lambda by D. From the intercept we obtain the size, and from the slope we obtain the strain value. This is very simple actually. Okay, and what I want to say you that this particular simple method provides the size as well as strain, and it is found that that later if we find out the size and strain by other different methods, then also the obtained value is almost matching. Okay, so that signifies the fact that Williamson-Hall method is not, Williamson-Hall method is one of the simple and best technique of obtaining size and strain, intrinsic strain value inside the nanocrystal. Now there are some generally we modify the models actually. So UDM model considers the homogeneous or isotropic nature of the nanocrystals, where the strain is uniform in every crystallographic direction. But this is not the case for a real crystals. Okay, this is uniform strain deformation model. This modifies. This is another model which use the anisotropic term. Anisotropic term means it does not use the uniform strain in every crystallographic direction. it considers that there are some non-uniform strain in every crystallographic direction. And in this uniform stress deformation model, or this particular model considers some stress deformation in every crystallographic planes, and putting the stress value which is related to strain actually here, that here the y scale is coming into the picture. This is nothing but our Young's constant. So that here Young constant is also related to every particular plane. Here it is not visible. This is HKL actually. So again, plotting into the same way, we can obtain the size and we can obtain the stress also. So uniform deformation model provides the strain value. Here also we can obtain the stress value, but from the stress sigma y scale stress value we can also obtain the strain value. Now there are methods of obtaining the y scale value that I don't want to discuss here. It is different for different pattern. I mean, different. This particular value is different for FCC. The y scale value is different for BCC also. That is a different issue. But we can obtain generally the value of strain and value of stress also. Similarly, replacing the energy into the system. Here the sigma is coming to the picture, but it should not be here. It is U. So that energy deformation model considers the uniform anisotropic lattice strain in all crystallographic direction and causes the uniform anisotropic lattice strain is the density of deformation energy. So in the same way, we can obtain the energy density by plotting the plot actually. Okay. So what I want to say you that by using different models of the Williamson-Hole method, we can obtain the stress, we can obtain the strain, we can obtain the Young modulus, we can obtain the energy density of the that are present in a nanoparticle. Obviously, these are nothing but the average of all the nanoparticles, but we can say that that exists inside the nanoparticle, the intrinsic strain, the internal stress, the internal energy that we can obtain from the Williamson-Hole method. Now, another method is there, what is called Helder-Wagner method. And in that Helder-Wagner method, the exact peak profile has been considered or assumed as a Lorentzian function. Okay, whereas profile has been considered as a Lorentzian function, whereas strain broadening as Gaussian function. So what I want to say you that here in the X-ray diffraction profile, the size should be one term is missing. Size has been assumed as a Lorentzian function, and strain broadening has considered as a Gaussian function. Okay, so XRD peak is neither, but the XRD peak is neither Lorentzian nor Gaussian. Generally, we observe that because in one particular XRD peak, suppose the peak is very smooth, then Gaussian pattern maybe we can associate. But in the case of a Gaussian pattern, if the peak position is matching, then tail may not match. Okay. Whereas it is observed that for a Lorentzian function, the tail is actually matches, but peak is not matching. So we generally take the mixture of Lorentzian function and Gaussian function, and a Helder-Wagner method assumes the shape of the peak profile as Boyd function, which is nothing but the convolution of Lorentzian and Gaussian function, which gives us a more realistic result. Okay, and there is a formula, a complicated formula is there, and we use every term is known actually. Epsilon is the strain, D is the lattice spacing, and D is the size. So every term is known. Okay, so plotting these, we can obtain again the size and the strain value from the Helder-Wagner method. But this particular Helder-Wagner method considers the lower angle diffraction pattern perfectly. but higher angle diffraction pattern it does not consider generally. That's why if the diffraction patterns which has all the diffraction peaks in the lower angle side, then Helder-Wagner suitably can be applied. And because of this, Helder-Wagner provides greater details about the strain value in the extra diffraction pattern. Again, there is a variance method, which is a Boyer-shaped method, but it considers the whole diffraction pattern, not considering only the lower part. The Helder-Wagner method considers well the lower part, but variance method considers the whole pattern effectively. And there is a complicated formula that have been obtained. Using this formula and plotting the terms, and we can obtain the size and strain value also from the variance method. Now, see, every particular whether it is a Williamson-Hull method, it needs a greater details to talk about. Whether it is a Helder-Wagner method, every details I need to talk. So I just covering the whole part. That's why I am just going through the surface part of every method actually. Variance method, again, it needs the whole idea need to be discussed, but there is no time to discuss everything actually. So what I want to say is that I want to tell you that there are Williamson-Hull method, there are some Helder-Wagner method, there is a variance method. The three methods are there, which depends on the broadening analysis of the system, and thereby we can obtain the size and strain value from this broadening analysis of the axial diffraction pattern. Now, I don't want to go into the details, but what I want to tell you that AI is nothing here. That A, L naught or A, these are the Fourier coefficient that we can obtain from the Fourier transform of the axial diffraction profile after extracting the pattern actually. So fitting the axial diffraction pattern with either with a Gaussian function or with a Lorentzian function or with a Boyer function, which particular function matches well your diffraction pattern, that function must be Fourier transform, and from the Fourier coefficient we analyzing of the Fourier coefficient or plotting that particular Fourier coefficient in this particular where L naught is the column length actually, that need to be again discussed, because in the nanoparticle what we consider is that there are many columns are available in the nanoparticle. This is something different that I don't need to discuss here. But what I want to say is that using the column length, using the Fourier coefficient, and some sort of complicated details, we can obtain using the Warren-Warburg method the size coefficient and RMS state. Recently, we have communicated this particular paper, but what I want to say is that it is also possible from the Fourier coefficient part of the Fourier coefficient analysis of the axial diffraction pattern. It is possible to obtain the size and strain also. And that is another method, what is known as Bulger method, and it also considers the Fourier transform of the axial diffraction pattern, but it considers the shape of the profile in terms of Boyer function. Okay, only we plot the method by the Boyer function, pseudo Boyer function generally, rather I can say, which generally fits well in the case of a Boyer method. And again, by using the other complicated terms, we can obtain the size and the strain value of the diffraction pattern. So this part is something different regarding the size and the strain value. Now let us go into some smaller details. What are the details? This is morphological index that we can obtain from the axial diffraction pattern. Some little bit of structures coefficient, some lattice constant we can obtain, Lorentz factor, Lorentz polarization factor, all the details that are available or that can be obtained from the axial diffraction pattern. What I want to say is that morphological index is the structural parameter which is generally used to understand the interrelationship between surface morphology and the particle size of the material. That also can be obtained. Structure coefficient is one of the important structural parameter for the study of the particular crystal planes. Okay, so structure coefficient mostly provides the quantitative information regarding the crystal orientation. That is also can be obtained in the case of a powder diffraction pattern. Now, one of the important parameter is lattice constant. Suppose if we have a simple cubic or FCC or BCC pattern or crystal structure is available, then we have the lattice constant A. That value can be determined from the Bragg's formula, okay, or more errorless. That lattice constant can be obtained from the Nelson relay plot. Okay, in the Nelson relay plot, it is the error, rather we can say errorless method of obtaining the lattice constant, and where we use the particular function, error function, Nelson relay error function f theta in terms of h scale, okay, and that relates to the theta actually. So f theta that relates to theta, and we plot that lattice constant from the lattice constant value from the Bragg's formula and Nelson relay function. We put the Nelson relay function value, that f theta, along the x-axis and lattice constant value along the y-axis, and extrapolating the particular plot to the value of f theta tends to 0. So f theta tends to 0 value gives us the errorless lattice constant value. You see, lattice constant value is a bit higher and a bit lower for higher angle side. But if we go for f theta tends to 0, then it gives us errorless lattice constant value. So by Nelson relay plot method, we can obtain the lattice constant value from the X-ray diffraction pattern. Okay, there are also Lorentz factor, Lorentz polarization factor. These are some factors that also plays a major role in the X-ray diffraction peak intensities, and that also can be obtained because if you take the X-ray diffraction pattern of your sample, bulk sample, and then if you take the X-ray diffraction pattern of your nanoparticle sample of the same material, then there may be a vast change in peak intensities, or rather we can say that if we have a sample and after doping, if we take the X-ray diffraction pattern, there may be a change in the peak intensities. So these they are the Lorentz factor and Lorentz polarization factor play the role in the peak intensities, and those factors can be obtained from the X-ray diffraction pattern. These Lorentz factors are there, Lorentz polarization factors are there, and that can be easily obtained actually if anyone go through the literature. That's not the issue. Now, one of the important part that I want to tell you regarding the Rydberg refinement, and this is very important, rather I can say in the X-ray diffraction pattern analysis. And we do the Rydberg refinement. This is a very, rather I do not say it is a complicated one, but it needs lots of practice to get the hand in Rydberg refinement. Okay, and we do the Rydberg refinement through, there is a typing mistake of the full proof. So there is a software, the different softwares are there, but there is a well-known software what is called foolproof software, and using that foolproof software we do the Rydberg refinement. What is the Rydberg refinement actually? That after Rydberg refinement, considering a known diffraction pattern or CIF file, we match our obtained diffraction pattern with the Rydberg refined pattern. And in the Rydberg refined pattern, if some peaks are deviated from the refined, the CIF file pattern, then you can say that your obtained pattern is not matching. See here in the case of this is the X-ray diffraction pattern of our CDSA nanocrystal that we have prepared, and the diffraction pattern is matching well with the refined pattern. Okay, so every peak is matching, and this matching is very required. And in the refinement, we obtained the crystal structures also, the standing lines also. All the standing lines that are actually available in the case of that particular material. And there are some background also we can obtain in the case of Rydberg refinement. Earlier I have told you that background is very important. So here background matching is also required to be furnished. Now, what important part that I want to tell you that after Rydberg refinement, the parameters that we can obtain from the Rydberg refinement file. Okay, we may obtain the Rydberg refined file, and we can obtain some parameters. That parameters can be fed into the density functional theory, what we have used in a few cases of our research paper. We fed the lattice structural information into the density functional theory, as well as molecular dynamics pattern. Recently, we have molecular dynamics related paper we have just communicated. So the Rydberg refined parameter, or Rydberg refined parameter or pattern provides you some parameter that can be fed into the DFT analysis, or that can be fed into the molecular dynamics analysis, which is useful for further study of the X-ray diffraction pattern. I mean, what I want to say is that our X-ray diffraction pattern is giving us all the details which can be fed into other software for obtaining other study. So that's why I want to say that the X-ray diffraction pattern is very important. Okay. Hello, Krishna sir. May I proceed with the atomic force microscopy, or let me stop here?
Sir, you can proceed shortly. It can be possible, sir, within a short period of time, or it will take long time, sir.
Yeah, very briefly, I shall cover up this atomic force microscope. Okay.
Okay.
Okay, thank you. So let me give you a very small overview of the atomic force microscopic analysis. Okay, and without going into the details, I want to say you that in the atomic force microscopy there are two methods. One is contact method, another is non-contact method or tapping method. And there in the atomic force microscopy we use the principle of van der Waals force. Where we use the van der Waals force, actually there is a cantilever. Is there in the AFM. That cantilever is available in that particular portion. Okay, and we place the cantilever on the we place the cantilever on the surface of the sample. But one very important thing I want to say you there. While studying the AFM analysis, that sample should be very smooth, and that's why generally for thin film structure analysis we use the AFM study, and what we do is that out of our nanocrystalline solution sample, we prepare a thin film of the solution, and after drying out, we do generally study the AFM analysis of that particular sample. So in the what I want to tell you that the cantilever may we use after touching the sample, or we may not touch the sample. And the cantilever actually that particular tip have almost around angstrom size range. and there is a laser beam that falls onto the cantilever, and there is a photodetector that detects the cantilever movement. So when the cantilever scans over the surface, the photodetector actually detects the movement or vibration, and thereby it scans, and you see the cantilever dimension. I mean, there is a tip available in the cantilever, and that cantilever can be placed over the surface of the sample. It may be a contact mode or maybe non-contact mode. Okay, but generally we do study with non-contact mode, because if the surface is not very smooth, then the tip may be get destroyed, which is very delicate, and tip is very costly also. Okay, so we go for non-contact mode study of the sample, and as we know that when at very close distance, due to the interaction or exchange force interaction, what we call van der Waals force, the van der Waals force play the role in scanning or in vibrating the cantilever actually. So through this principle, the cantilever scans the surface. Okay, this is the contact mode, and there is a non-contact mode also. So what is known as taping mode. If the surface is not very smooth, or if the thin film surface or nanoparticle surface is like this, nanoparticle, not the single nanoparticle surface, but as a whole, the thin film of the nanoparticle surface, the cantilever actually moves like this. Okay, and the photodetector detects the movement, and thereby it scans. And here you see the AFM provides the 3D profile view of the nanocrystals. Okay, the 3D profile view is very important to see. And what I want to say is that AFM is far more sophisticated than electron microscope, because the resolution is much higher in the case of a AFM. If we go for contact mode, the resolution is quite high, and the magnification is also quite high in the case of AFM analysis. AFM also provides the surface texture, roughness, waviness, and spacing of the surface. Actually, AFM provides the smoothness or roughness of the thin film, but we also use it for nanoparticle surface also. And this is one example of our prepared nanocrystals, DSC nanocrystals. You see the beautiful pattern that we have obtained, or it is showing the crystalline, I mean showing the height profile of the sample, AFM image of DSC nanocrystals. And these are the height profile or texture or waviness that we have obtained in the AFM analysis. And very briefly, I have covered the AFM, because earlier I understood that after covering the XRD pattern, the whole things of AFM is cannot be discussed in details, because it needs a whole lot of things. The principle of AFM is complicated, though it is a very small, but greater details into the rigorous details are required to know. If the theory part is a little bit complicated, but on the surface, what I want to tell you that getting the structure or getting the waviness is very simple in obtaining while starting through AFM. Thank you very much. Krishna sir, thank you.
Thank you, Ratanda sir, Department of Physics, Tripura University. It was an wonderful lecture and inspiring for our young researchers, and all of us got benefited by your lecture. So once again, thank you, sir, for your wonderful lecture. Now thank you, sir. Now there will be a question answer session, and I request all the participants to write their doubts and queries in the chat box. So now
Yes,
the
yes.
question answer session starts. Subhash sir.
Was sir,
Yes.
you asked some question. The question already put it in the chat box, I think. Please copy from that chat box and ask our person.
Hello, good afternoon.
Hello.
Am I audible?
Yes, yes.
Dr. Ratan Das. Sir, we have some questions.
Yes, yes.
Our students as well as some participants have asked. So first question, what we received in the chat box, it is Miss Anuradha Sharma. She wants to know how X-ray is having dual nature.
I beg your pardon. Please tell me the question again.
How X-ray is having dual nature.
Dual nature.
Yeah. Whether I think
Okay, okay, I understood. See, this is a quantum mechanical phenomenon. So generally we say X-ray is a wave, but at the same time, just like light that we consider that the X-ray is a photon also. So this is a quantum mechanical part, and just like light, just like electromagnetic wave, X-ray is the electromagnetic wave, which is a dual nature actually. So it depends. It depends on the experiment in which way we can use it. Suppose in the case of an interference, if we go for the diffraction pattern in the X-ray, then we have to consider the waviness or wave nature of the X-rays. Again, if we go for the quantum scattering experiment, we have to consider the particle nature of the X-rays. So my curiosity is that sometimes students are very curious to know. Suppose I have a diffraction experimental setup where I am throwing an X-ray and we are getting the diffraction pattern. Now putting or keeping the X-ray, if we replace the diffraction experiment by a quantum experimental setup, we may obtain the quantum scattering. Okay, so the same X-rays is giving the quantum scattering, and the same X-rays is giving the diffraction pattern also. It is a dual nature. It is a quantum mechanical phenomenon, and it is not as our wish that sometimes as our wish we can use it as a wave, or sometimes we can use it as a particle. It is the manifestation of the nature or manifestation of the wave that it reflects its wave nature. It reflects its particle nature also. Maybe that I am able to understand the question. I am able to give the answer.
Yes, sir. Thank you very much. Sir, kindly you share the screen. Stop sharing, please.
Okay, thank you. Okay.
Stop sharing. You will see the questions also. Okay, another question, sir. Is it visible, Dr. Ratan Das?
Yeah, it is visible.
Okay. Another question. Dr. Prasenjit Rai, who has put on question, can this technique be used for gen toxicity studies? So gen toxicity, I think it may be genotoxicity, which is related to say some chemical agents that damages genetic information within the cell, causing mutation. So such informations, can it be possible to study
See, see.
using X-ray?
At the beginning, I have told that if any sample is having crystalline in nature, that may give you the signature of the crystallinity. Or if any sample, if it has a amorphous nature, then it gives it the amorphous nature in the X-ray diffraction pattern. I do not know the material. I do not know about the material. But if it is crystalline in nature, obviously it will reflect its nature or its signature in the X-ray diffraction pattern. Whether it is a biological sample, whether it is a chemical sample or anything else, if it is crystalline or amorphous, it must be reflected in the X-ray diffraction pattern. Suppose if I have a vegetables, if I dry it and if we take the X-ray diffraction pattern, some sort of signature we shall obtain obviously in the X-ray diffraction pattern of the vegetable, dried vegetable material.
Okay. Sir, another question from our HUD sir. He has some queries because he is dealing with nano particle characterization for a long time.
Yes.
He has some question. It is two questions. Is it necessary to match all peaks of a powder sample with a standard PDF number? So followed by this, he has another question: how to calculate FWHM from the XRDP? So I think you are a physics person. You can explain this thing, because as a chemist, we don't know these things properly, sir.
Yes. Let me explain briefly the first question. If you take the XRD pattern of an unknown sample, a little bit known, because suppose if you are going for taking the XR diffraction pattern of a little bit known sample, because you are preparing the sample, you are not obtaining unknown sample from the moon or unknown sample from the Mars, but we generally do prepare a known sample. So as per our knowledge, we may match. I am explaining a little bit. So whenever we get a X-ray diffraction pattern of our little bit known sample, it should match with the standard diffraction pattern. All the peaks should match with the standard diffraction pattern. Some peaks may be missing, that does not affect. But if there is a peak which is not matching with the standard diffraction pattern, then there may be a problem. Because in that case, your sample may be contaminated, or may be doped, or maybe something else, or it may consist of something else. Suppose I have a silver sample, suppose I have a CBS sample. If the sample is contaminated, then hugely contaminated, then some extra peak will appear which will not match with the standard diffraction pattern. But if we have a diffraction pattern where some peaks are missing, some peaks are not available compared to the standard diffraction pattern that are available in the software, then it harmful. It doesn't matter, because all the peaks may not be available, all the planes may not be available in your obtained standard diffraction pattern. Regarding your second question, Fullerton half maxima. Fullerton half maxima that can be obtained if we plot the X-ray diffraction data in Excel or origin software, and placing the cursor that I have to show you. I do not know how to show you. Placing the cursor on that particular pattern on the plot, you may obtain the data of the two ends of the Fullerton half maxima, and the difference will give you the Fullerton half maxima part.
Thank you very much, sir. Thank you.
Thank you very much, sir.
Use Excel, or if it is I generally use Excel. But here in the Tripura University, many people use Origin software. My student also use Origin software, but throughout my career, still I use Excel for plotting the Excel diffraction data actually.
Okay. Another question is from Priyam Nath Bhumik. Which is more effective for surface study, Raman or FTIR or AFM?
See, AFM gives you the morphology. Morphology means what does that surface actually means by that the student I do not know. But surface, if you tell about surface, then in the surface there may be a layer of chemicals. Suppose if we have a nanoparticle surface, the nanoparticles may be covered by some agent to stabilize the nanoparticles. It is required to stabilize the nanoparticle by covering the by making a layer out of something, some agent, what is called ligand. Okay, those ligands or stability of those ligands or stability of the nanoparticles can be studied from FTIR. Okay, what are the agents are available, which bond is created with the nanoparticle surface, that we can study through FTIR. But when I go to the AFM study, as a whole, the big surface we study, we do not study the chemical layer on the surface. The chemical layer cannot be visible to the AFM. Okay, and Raman does not give us any signature of the surface, a visual structure of the Raman pattern actually. Raman pattern actually give us sometimes Raman also give us strain. Raman gives us the vibrational spectra of that particular sample. So many things we can obtain from the Raman. But generally, I want to say you that for morphological analysis, for surface structure analysis, as a whole, the bigger surface will use the AFM or a scanning electron microscope. But FTI study is used for the chemical bonding of some ligand to the nanoparticle surface.
Okay. Another question from Anuradha Sharma. She is JNB PGT from PGT JNB Mana Raipur. So, is X-ray diffraction method applicable for liquid crystal also? I think
Yes.
This is applicable.
If people are using liquid crystals, this is a crystals, and people are using acceleration pattern of the liquid crystals.
Yes. Without X-ray diffraction, we cannot get the actual structural idea of liquid crystalline method. Another question, it is put forward by Sudeep Pal. How to prepare a nanocrystal and what are the methods available? I think it's difficult to explain within a short period of time how to prepare nanocrystal and different methods.
At the beginning of my lecture, I have told about that there are physical methods, there are chemical methods, there are biological methods of preparation. Physical methods are ball milling and lithographic technique, which are very costly. Instruments are very costly, and biological preparation is also very easy. I can generally suggest to many people use biological agent, use some plant extract for the preparation of the nanoparticles. But chemical methods are also very effective. I want to say that easy and simple methods are the chemical method, wet chemical method, through which we can prepare the nanoparticle easily.
Any more question?
I think there is no more question. Okay, but I just have some query. Is it possible to know the particle size? Okay, one more question from Priyamnath Bhumik. Is it possible to know the particle size from atomic field microscopy?
Yeah, actually, in general, we use the height profile in the AFM analysis, but using while doing the atomic force microscopic study during the in situ study, we may get almost the width of the nanoparticle. No, it is difficult. It may not match with the electron microscopic study, but somehow it may match, or somehow we may obtain a general idea about the size of the nanoparticle after measuring the width in the pattern.
Question.
Yes.
I think we have crossed our time. I think no
Yes,
more questions.
we have crossed time, but we are seeing there are many queries because Dr. Ratan Das has aroused many queries of our respected participants. Another queries are from Prasenjit Rai. In India, lots of research work are going on fly ash. Sir, what will be the role of AFM in the study of fly ash research? Can you have some highlight on this, sir?
Yeah. For AFM, you need to prepare a sample of thin film type. A smooth thin film type sample is required for AFM study. You cannot put the powder sample there. You cannot put a haphazard sample there because the tip may get destroyed. Even I want to say you here that if you prepare a sample for AFM, then it should be preserved very carefully, because if dust are available or dust get contaminated into the AFM sample, that may also destroy the AFM tip, even in non-contact mode. So AFM very sophisticated instrument, very sensitive instrument. I do not know how the student will prepare a film out of fly ash. If it is possible to prepare a smooth film out of fly ash, then it is possible to study through AFM.
Okay. So, sir, another question. Probably this is the last question.
It's the last question.
From Paramita Chakraborty. Sir, how nanoparticle help in remediation of hydrocarbon polluted soil?
See,
Hydrocarbon polluted soil.
okay. I do not know what is that hydrocarbon polluted soil. I am not part of this. My research part is not related to this. But I want to say here that the application range of nanoparticle is huge, starting from biology to atmosphere, everywhere. So there may be a remedy. I can hope that there may be a remedy. There may be applicability of nanoparticles in that particular area. I hope so.
There is your question, madam. Confident, madam. I, I think yes, that was the last question. So it is the time for vote of thanks to our research person, Dr. Ratan Das, who explained nicely, and he has taken so much pain to talk one 1 hour, 1 and 20 minutes, 1 or 20 minutes. So I request Dr. Subhash Devnath give a vote of thanks to the Dr. Ratan Das. Subhash sir, please.
Once again, thank you, Ratan Das sir and Shubhas sir for the nice question and answer session. And the participants, if you have more queries, you can personally contact to our Dr. Ratan Das sir. Sir, if you can share your mail to the participants, if permissible. And now the vote of thanks will be given by our departmental colleague, Dr. Subhash Devnath. So, sir, please.
So I thank our honorable principal sir for encouraging us to hold this webinar, national webinar. So first day we have completed it by, and I thank our IQSC coordinator for coordinating entire session. Especially, I thank Dr. Devashish Sharma, Assistant Professor of Mathematics, who have done this job very nicely. I thank our HOD sir for taking initiative in every aspect to complete this webinar. Actually, this is the brainchild of our HOD sir, Mr. Krishna Chandra Das, who have initiated this webinar, national webinar. I also thank our convener, Madam, Ms. Sarvasri Nath, who have conducted this session very nicely, and not interruption. Actually, interruption happened in many aspects in regarding related to our network problem. Anyway, I hope tomorrow's program will be also a successful one. The program has impact to the participant. We have seen it through our different comments. Our special thanks to our mentor, Dr. Tushardev Kanungo, who has helped us in many ways. Thank you very much. Thank you all.
Once again, I thank the speaker of the day and all participants. All participants are requested to submit the feedback form given in the chat box. Tomorrow again, we will assemble at 11 a.m. sharp. Stay safe, stay connected. Thank you once again. Thank you. Thank you, sir.